So meanwhile, while the Peace Day flow is active, the Peace Day flow is entering a tube system in here, traveling down slope, going off in this direction. While this was active, there were spatter cones that grew on the floor of Pu'u'o crater, and small flows from those spatter cones refilled the shallow basin that had formed in Pu'u'o, refilled the crater, and began to overflow from the sides of the crater. Now, the most dominant of those spatter cones was this one here. It's on the northeast side of the crater floor. We just call it the northeast spatter cone. It formed this pretty large composite cone feature, and flows were able to directly feed from this spatter cone out its top and then flow straight out of the crater down the crater's flanks. January of last year, those flows, that spatter cone, actually it's not this. This is the bigger cone in the background, but spatter cone is in front of that. This spatter cone began to feed lava continuously down the north side of Pu'u'o and began feeding a flow which we call the Kahauale'a flow. And that's this flow here, of course. The Peace Day flow is this line of fume you can see here, extending off in this direction and then goes out toward the ocean off in here. This Kahauale'a flow was active for the next few months, and eventually it reached out to about 3 miles from Pu'u'o before it stopped in April of last year. Though it stopped, within a few weeks, a new flow from the same place, from the same spatter cone, began, headed off toward the north, directly north of Pu'u'o at this time, entered the forest north of Pu'u'o, and then began to parallel the earlier Kahauale'a flow, which is right here, began to parallel that flow and extended off toward the northeast as it moved. We call this the Kahauale'a 2 flow. It was the second of this pair of flows. So as this Kahauale'a 2 flow developed, the Peace Day flow, which had been entering the ocean down here, began to wane. Pu'u'o sits right here. Peace Day flow did come down, enter the ocean. Ocean entry died. Activity began to back up slope. And by October of this past year, activity was really focused on a few small breakouts on the upper part of the flow field, just a few miles from Pu'u'o. You can see this slightly reddish color in here. These are those breakouts. By comparison, the Kahauale'a 2 flow is all of this reddish coloration here. This is an infrared satellite image. So all the flows show up as these hot red features. So the Kahauale'a flow essentially pirated all the supply from the Peace Day flow, and in November, early November this past year, just a few months ago, the Peace Day flow died. The Peace Day flow, or the Kahauale'a 2 flow, now continues to be active. It's still extending toward the northeast from Pu'u'o. This is from our overflight on December 26th. A few weeks ago, the last overflight we had, we got to go out and check things out. The flows were about 4 miles to the northeast of Pu'u'o and very slowly advancing into the forest. This is a satellite image, infrared, and this is a Landsat image taken the same day as our last overflight, December 26th. And you can see, here's Pu'u'o back here. The yellow line is the outline of the Kahauale'a 2 flow, and you can really see how this activity is focused and kind of spread out, but really focused out near the end of the Kahauale'a 2 flow. And in here I have this is the lava tube, which is feeding those flows. And so this actually extends out, at least out as far as where this big patch of activity starts. Now we've plotted up the front position of the flow. It's straight line distance from Pu'u'o, so very simplistic, but just the straight line distance from the vent of where the most distant active part of the flow is. And we've plotted this up over time. So this is distance, this is time. So this shows you that the flow has been advancing with time. And if you draw just a crude straight line through these points, there are some changes, some variations. If you draw a straight line through this, the flow has been advancing at about 100 feet per day. So it's advancing at a very slow rate. All right, so just to recap this, for the period March 2011 until essentially now, we had the Kamoa eruption, which is this flow right here, and a little patch right in here. We have this flow right here, which was the August 3rd breakout, the very fast-moving abrupt breakout from the west flank of Pu'ua'o. The Peace Day flow covered this area shown in red here. Then the Kahauale'a flows are these flows which extend off toward the northeast. Now the transition from the Peace Day flow as the dominant flow to the Kahauale'a flow as the dominant flow marks a very important transition in this eruption. And this is why. The rift zone is essentially a ridge, is a topographic high. On the south side of the rift zone, downhill is this direction. North of the rift zone, downhill is this direction. The Kahauale'a flows, most flows at Pu'ua'o over the years, mostly have gone south of the rift zone. They've caught the steep slope and went into the ocean along the southeast coast. The Kahauale'a flows are north of the rift zone, and they're extending in a direction from which downhill is this direction. Now in gray here is we call it a lava shed. It's like the watershed or the drainage basin for this area. This is, if this was a stream valley, all the streams and tributaries would flow down and stay within this, in this gray polygon, and it reached the ocean down here. So you can see that this flow would likely stay within this drainage basin and continue down slope. Now we can improve upon this by the magic of computers. This is a flow path map. I've just called it a fuzzy flow path. It's because it takes into account a lot of noise in the topographic surface. The way that this is built is by taking what we call a DEM, a digital elevation model. You can think of that like a photograph of the ground surface, but instead of the pixels being color values, those values are elevation. So we can write, we can write computer programs, and we pick a starting point where the flow is active, and we have a pixel, and we know that pixel's elevation. We write a program to then look at all the pixels which surround that one pixel and choose the pixel which is lowest in elevation, and then move to that pixel. And then again, look at all the pixels around that second pixel, choose the one which is lowest, move to that pixel, and so on. And by doing so, you can create a series of pixels which defines one potential flow path. Then what we do is we come back and we take the entire DEM and we randomly add either plus or minus 0, 1, or 2 meters. Think of this 0, 1, or 2 yards. Just randomly add a little bit of elevation noise to the entire DEM and then run the flow path again. And that noise will cause the flow path to be in a slightly different place. And then we'll start over with the original DEM and again randomly add some noise and run a third flow path. And for this, we did 50,000 runs. And so what it shows is that the areas in red are those areas which were inundated, or which were, we'll just say inundated, most frequently during all of those runs. And as you go into these slightly orangish colors and the yellows, we're getting into those pixels which were inundated the least often. So it basically shows you kind of a broader view. Rather than a single stream line running down, it gives you a broader view of where the flows are most likely going to travel as they travel down slope. It's also convenient because it adds some slop to the situation, because lava flows don't behave like rivers. They make their own topography, they spread out, you have starts and stops, you have breakouts. And so this kind of builds in some of this uncertainty that is a given for Pahoehoe lava flows. Now, as the flow comes down, there's a few places here, here's this drainage, the edge of the drainage here. Down in here, this flow path gets pretty close to the edge. Now, you can imagine that if the flow is coming down through here, you get a breakout over here, that breakout would be able to jump over the flow boundary and get out into this flow path. So it gives us a way to look at where the most probable places lava might flow, but also gives you some of the additional information that might happen as the flow would develop into the future. Now, we wouldn't leave this as a static image. As this flow advances, we would keep rebuilding this to see how things are changing. And a lot of this is dependent also on the actual digital elevation model, the actual topographic surface, which is, you know, there are some uncertainties because there's forest out here and trees, you know, sometimes the elevation values that we get back, this is all from satellite or airborne imagery, sometimes those values are treetops and not the ground. So there are some uncertainties in this. Now, I'm also not saying that this entire area will be covered by lava. I mean, that's a huge area. You know, this is just, you know, to give an idea of what kind of worst case scenario, what might be possible. Now this, as I've shown here, this is where the flows would go. So let's look at the other factor, which is how fast. I showed you this before, but just this part of it. If we continue this line and use the current advance rate, about 100 feet per day, these flows in a straight line distance wouldn't reach, it would take a year, more than a year, for the flows to actually reach populated areas. And quite frankly, a lot can happen in a year. As you've seen throughout this talk, there are frequent changes on this eruption. Every few years, things change. And so, yeah, a lot can happen in a year. So this is not something to be aware of, but not something to be imminently worried about.